This is the lesson for 7.4, Solving Log Equations and Inequalities. As you can see in the PowerPoint, if we are going to solve a logarithmic equation or an inequality, we can either use the definition of a logarithm, that's the first bullet, and as you can see here, if you have log base b of x equals y, then of course the argument x has to equal the base b raised to the y. And so that's the first way we can go about solving a log equation, or as we're going to see in the last two bullets, that also applies to an inequality. By the way, the restrictions are the same restrictions we've seen before on logarithms. The base always must be positive. It can't be 1 because then it would no longer be logarithmic, and the argument must be positive. And as we're going to see when we solve inequalities, that will be something of significance. In the second bullet, where we have logs of the same base, log base b of x equals log base b of y, if the base is the same, then it's like the log base b cancels out, and we can set the two arguments, x and y, equal. Then we get to bullets 3 and 4. And in bullets 3 and 4, you can see if we have log base b of x is greater than y, right here, then we convert it to exponential form, and we say the argument x is greater than b raised to the y power. The inequality symbol remains the same as long as you write the argument first, and that's really important. If you flip it around and write b to the y first, then that would mean you'd have to reverse that inequality symbol. In the last bullet, we have log base b of x is less than y, which, by the way, these properties do hold true for greater than or equal to, less than or equal to. So when we go to exponential form, we get this first part that x is less than b to the y. But this is where we have to be careful. In an inequality, our solutions are on a continuum. We don't just get a specific solution or solutions that we can test by plugging back into the argument of the logarithm to make sure it is a positive argument. Since we're on a continuum and it's less than, we know we're going to get values of x that are negative because as we go to the left on the number line, we're going to go towards negative infinity. As a result, we need to put a firewall, which is this part, to ensure that x is greater than 0. Of course, it's flipped around so we can write a compound solution so that x is less than b to the y, but at the same time, to be valid, is greater than 0. So keep that in mind as we solve the problems below. You're going to see where that comes into play. All right. So I'm going to move down here. We have solve log base 9 of x equals 3/2. In this case, we're just a normal standard log equation, and I think we can use the exponential form here to help us. Of course, we want to write the argument first, so that would be x, and x is going to have to equal the base 9 raised to the 3/2. Of course, we have to remember how to evaluate that. The denominator of our rational exponent is 2. That's telling us the root that we need to take. And so that means that x is going to equal the square root of 9, all raised to the numerator of our rational exponent, which is 3. That means x equals 3 to the 3rd, or 27. And if you check that, that makes sense. Log base 9 of 27 equals 3 halves because 9 to the 3 halves would be equivalent to 27. All right, let's try our second one. In similarity to number 1, we have log base 1/10 of x equals negative 3. Again, exponential form is something we can use here. We're going to say the argument x equals the base 1/10 raised to the negative third. Of course, this is where we have to remember the reciprocal property of a negative exponent. The base 1/10, since it's raised to a negative exponent, we can take the reciprocal of that base, which would be 10, and raise it to a positive 3, which means x would equal 1,000. Good. Going on to number 3. So in number 3, this problem is not like 1 and 2. We have actually logs of the same base on both sides. Log base 5 of 3x minus 1 equals log base 5 of 2x squared. Since they're both log base 5, that can cancel out, and we would set the arguments 3x minus 1 equal to the argument 2x squared. Now, the question you have to ask yourself here is, what type of equation are you solving? Is it linear? I don't think so, because it cannot be written in slope-intercept form. Is it quadratic? Hopefully you recognize it is quadratic. It can be written in the form ax squared plus bx plus c equals 0. I typically like to leave my squared term positive, so I'm actually going to make the left side become 0 by subtracting 3x from both sides and adding 1 to both sides, so that I have 2x squared minus 3x plus 1 equals 0. At that point, I have to consider the ways I can solve a quadratic. There are 2 ways that I consider. One is factoring, the other is quadratic formula. My first go-to is factoring. Why? Because it's the most efficient, and on a time-constrained test like the SAT, probably the majority of quadratics will be factorable, and it's going to take you less time. So I'm going to try reverse FOIL. I know for the first position to be 2x squared, 2x and x would have to be what I use. And for the last term to have a product of 1, it would be 1 and 1. Checking my outside product, that would be 2x, and my inside product 1x. And that does have a sum of 3, because remember, that's what we're looking for. And so the good news is it works. And so I just have to get my signs. They're both going to need to be the same and both be negative. And when I set those factors equal to 0, which hopefully you remember this, I'm going to get 2x equals 1, which means x is 1/2. Or I'm going to get x equals 1. Now, you do have to be careful here. I need to make sure that these solutions never make an argument negative. In 1 and 2, since I was solving for x and x was not negative or 0, I was okay. But in 3, the arguments are quantities, 3x minus 1 and 2x squared. So let's start with 1/2. 3 times 1/2 would be 3 halves. Minus 1 would be, that's really 1.5 minus 1. That would be positive 1/2. Of course, if I plugged 1/2 in on the right side, squaring it would be positive times 2 is positive. So x equals 1/2 would be valid. If I try 1 on the right side, no problem. On the left, 3 times 1 minus 1 also would be positive, so both solutions are valid here. Moving on to 4. Since they'll mix all of these together, we're back to a log base b of 9 equals 2, we only have a log on one side, so I'm going to use exponential form. And in this case, my argument is 9, and that's going to equal my base b raised to the second. Of course, how I'm going to solve that is taking the square root of both sides. And when I take the square root of both sides, I'm going to get b equals 3. It won't be plus or minus 3 because the base can't be negative. So b just equals positive 3. Number 5. Now I'm dealing with a log inequality. Again, I'm going to use exponential form. And here, x, the argument, would have to be greater than the base 4 raised to the third. The good news is we're on a continuum to positive infinity, so I don't have to worry about x becoming 0 or a negative, so that's fine. I just need to cube 4, and that would mean I'd get x is greater than 64. How about number 6? Similarly, I can go to exponential form. My argument x would be less than or equal to 8 raised to the negative 2. Now, in this case, I have to be alert because my answers are on a continuum to negative infinity, less than or equal to. So this is where I do need the firewall, and I'm going to include the firewall and say that x would have to be greater than 0. So that's putting that on this end. Let me get that looking a little more like an inequality symbol. And then I still need to finish this. And so I would have 0 is less than x is less than or equal to 1 over 8 squared, or basically 0 is less than x is less than or equal to 1 over 64. So the firewall is really important when that inequality symbol is less than or equal to when you go to exponential form. Not as much of a concern in number 5 because the inequality was greater than. Of course, sometimes when you solve, you can get some flipping of inequality symbols, so you just have to be alert. Number 7. Our argument is 2x minus 1. We can use exponential form. I'm going to say 2x minus 1 is less than or equal to the base 3 raised to the second. Do I need a firewall? Well, the inequality symbol is less than or equal to, so the answer is yes. I have to say that that is going to have to be greater than 0, and then I'm going to be able to solve. And so I'd have 0 is less than 2x minus 1 is less than or equal to 9. Of course, I'd add 1 to both inequalities. So 1 is less than 2x is less than or equal to 10. And then I would divide both inequalities by 2. So I'd get 1/2 is less than x is less than or equal to 5. So now I've solved number 7 with the same high alert that I had in number 6, again because of that inequality symbol. And you just have to be really alert for that so it does not become an issue for the argument becoming negative or 0. Number 8. These are two logs of the same base. Log base 2 of 3x minus 5 greater than log base 2 of x plus 7. Since the bases are the same, I can set the arguments in the same relationship and say 3x minus 5 is greater than x plus 7. And if I go to solve that, that means 2x would be greater than 12 and x is greater than 6. So if I test values to the right of 6, you're going to have a number that's greater than 0 for x plus 7. And 3 times 6 is 18 minus 5 would be greater than 0. If you increase that to 7, because it can't equal 6, but 7, 3 times 7 is a larger number, 21 minus 5, I think we're fine. But to be certain that we have no problem, we can take each argument and set it greater than 0. And if I solve, that means 3x would be greater than 5, and x would be greater than 5/3. Certainly 6 meets that condition. And then if I set the other argument, x plus 7, greater than 0, x has to be greater than -7. So we have to go with the larger one, which is this one. But 6 already is greater than 5/3, so we don't have an issue. That is our solution. But let's see what happens in number 9. Number 9 is very similar. We have log base 8 of 2x is greater than log base 8 of 6x minus 8. Logs of the same base, so we're going to set 2x greater than 6x minus 8. And I don't care what way you solve this. You might decide to subtract 6x from both sides. That would mean -4x is greater than -8. Of course, then we have to divide by -4. And when we do that, we are going to have to flip our inequality symbol, and we'll get x is less than +2. Since I flipped that inequality symbol, that's where I have to be on high alert, because I'm heading to -infinity, and it's very possible that's going to create a problem. So I'm going to do what I did in the last problem. I'm going to take each argument and set it greater than 0. If I divide both sides by 2 here, that just means x would have to be greater than 0 on the left. On the right, when I set 6x minus 8 greater than 0, 6x has to be greater than 8, which means x has to be greater than 8/6 or 4/3. We have to go with the larger value to ensure both arguments are positive, so that's my firewall. And I'm going to flip that around and put that on my solution and say x has to be bigger than 4/3, yet less than 2 to be a solution. And this is my solution. Notice that looks considerably different than what happened in problem 8. We had the issue because of this less than, and that gave us that firewall that we have to be alert for, particularly when the solution is heading towards -infinity. So that's your lesson on solving log equations and inequalities. We're using the properties at the top on the PowerPoint slide, and the homework you have is right here. It can be found in Canvas, page 480 to 481, 8 to 19 all, 22 to 30 all, and 33. Please be reminded that next Monday and Tuesday we will be quizzing over sections 7.1 to 7.4. We're going to split it up Monday and Tuesday. On Monday, we're going to actually focus on graphing both exponential and log functions. That would be the graphing part in 7.1 and 7.3. And you want to also make sure you review domain and range. All right, hope you have a great day, and we will see you soon.